Analysis of standard second order system. So the transfer function of a standard second order system is given by omega n square upon s square plus 2 zeta omega n into s plus omega n square. This is a standard second order system. See, just convert it into unity feedback configuration just like this. How will you get the unity feedback configuration? What is the formula that you need to use? It's not just a formula, there are various ways you can get unity feedback configuration of any particular transfer function, right? So tell me what has to come in this box. It is omega n square divided by s into s plus 2 zeta omega n, right? This is R of s is the input here and C of s is the output here. So this is equivalent to this. This particular system is exactly equivalent to this. So we have to analyze this particular system using our time domain analysis techniques. Yes, very good, Upmanyu. It is omega n square upon s square plus 2 zeta omega ns. Yes, very good. Therefore, this is our standard second order system. So the standard second order system, when fed with various inputs, that is what we need to analyze, right? So here the most important input as far as second order systems analysis is concerned is only unit step input. We are not bothered about unit impulse input or else unit ramp input, right? So focusing on your GATE curriculum, so the analysis of step response of the analysis of step response of your second order systems is only of our concern. Therefore, let us analyze it for unit step input. Unit step, right? So in order to analyze this for unit step input, that is C of s, if unit step input is provided, R of s will be is equal to what? That will be is equal to 1 by s. Then C of s will be is equal to R of s multiplied by the overall transfer function. That is how much? It is omega n square divided by s into s square plus 2 zeta omega n into s plus omega n squared, right? So in order to just expand this, you have to convert this into partial fraction form. A by s plus bs plus c divided by s square plus 2 zeta omega n into s plus omega n square. So can you find out the values of A, B and C and let me know. So I have already explained this procedure while analyzing the first order systems, right? If at all you want to obtain the unity feedback configuration of a first order of any particular system, right? So this is the overall transfer function you have, and you have to convert this into a unity feedback configuration like this. So in order to do that, what you should do is you just have to find out this block, right? So this block is nothing but your open loop transfer function g of s, right? So g of s will be is equal to, from the overall transfer function, this overall transfer function can be written as some n of s upon d of s, right? G of s will be is equal to n of s divided by d of s minus n of s. D of s minus n of s, that is what I did. Numerator is omega n square and denominator is s square plus 2 zeta omega n into s plus omega n square. So s square plus 2 zeta omega n into s plus omega n square minus omega n square, you will get this. A will be is equal to what? A will be is equal to 1, right? B will be is equal to minus 1 and C will be is equal to minus 2 zeta omega n. So I am taking this minus 1 is common from this, so I'll get 1 by s minus s plus 2 zeta omega n upon s square plus 2 zeta omega n into s plus omega n square. So before obtaining the further analysis of this particular system, second order system, we just need to find out the roots of this particular quadratic polynomial, right? So can you find out the roots of this polynomial and let me know what are the roots? So in order to get C of t, we have to Laplace inverse on C of s. So please note this down and please keep it with you ready so that we can obtain the expression for its output C of t, right? So just obtain the roots of this quadratic polynomial. What is a quadratic polynomial? s square plus 2 zeta omega n into s plus omega n square, right? So this is nothing but the standard characteristic equation of your standard second order system. This is characteristic equation of standard second order system. Standard second order, right? So obtain the roots of this particular characteristic equation. What are the roots? So you can get the roots using minus b plus or minus root over b square minus 4ac by 2a, right? So the roots, what is a? A is equal to 1, b is equal to 2 zeta omega n, and c is equal to omega n square, right? So if at all you solve this, you will get these roots. It is minus zeta omega n plus or minus omega n under root zeta square minus 1. So these are the roots. These are the roots of this particular. S will be is equal to, what is minus b? It is minus 2 zeta omega n plus or minus root over b square. B square is 4 zeta square omega n square minus 4ac, 4 omega n square, divided by 2a, that is 2. So it is minus zeta omega n plus or minus 2 omega n under root zeta square minus 1 divided by 2. If at all you divide this by 2, you will get this. Yes, right? No doubt still now? Why we don't consider 1 by s part in C equation, characteristic equation? Chetkar Kumar, 1 by s is because of input. 1 by s is because of input. Characteristic equation of your system is given by your system's transfer function itself, purely from its transfer function, not from any other thing. Is it clear, Chetkar? Right? So these are the roots. So if you put zeta is equal to 0 in this, let us put zeta is equal to 0 in this. So case 1, let us say zeta is equal to 0. When zeta is equal to 0, what are the roots going to be? S is equal to what? S is equal to 0 plus or minus omega n under root 0 minus 1, right? Therefore S will be is equal to plus or minus j omega n. When zeta is equal to 0, the roots are plus or minus j omega n, right? Which means one root is going to be, see, if this is the S plane, I'm just showing the S plane here. This is which plane? This is S plane. So in the S plane, this is imaginary part of imaginary axis of S plane, and this is a real axis of S plane. Plus or minus j omega n means they are going to lie on the imaginary axis, yes or no? Therefore the roots are going to lie on the imaginary axis, j omega n, and another root minus j omega n, right? Just put S, let us just take zeta will be between 1 and 0. Case 2. In case 2, zeta is taken to be between 1 and 0. 0 less than, zeta less than 1. Right? If this is the case, what are our roots going to be? S will be is equal to minus zeta omega n plus or minus. See, zeta is something less than 1, then zeta square will be still less than 1. Something less than 1 minus 1, that will be a negative number, and a negative number under root. What happens when a negative number is taken under root? What happens? You can take this imaginary part to be this side, and you can write it as omega n under root 1 minus zeta square. So these are the roots in the case of zeta between 0 and 1, 1 minus zeta square. When zeta is between 0 and 1, the values of your roots are minus zeta omega n plus or minus j omega n under root 1 minus zeta square, right? So from this expression itself, let us frame out an important formula which we'll use in later classes, that is omega d, right? This omega n under root 1 minus zeta square, this is called as damped frequency of oscillations, omega d, right? We call this as omega d, that is damped frequency of oscillations, when you look at the response of your second order system, you will come to know why we called this as omega d. Is it clear? Right. So let us look at the third case. The third case is when zeta is exactly is equal to 1. See, we started at zeta is equal to 0. We have slowly increased the value of zeta from 0 to some value between 0 and 1. And now the third case we are going to consider is when zeta is exactly is equal to 1. Right? So when zeta is taken to be exactly is equal to 1, if you put zeta is equal to 1 in this, what are the roots you are going to get in the place of s? What are the values of s? If zeta is exactly is equal to 1, it is minus omega n, right? When zeta is exactly is equal to 1, this is minus omega n, whereas this part will be is equal to 0. 1 square minus 1 square, it is 0. Therefore, the roots are s is equal to minus omega n and minus omega n, right? The roots are repetitive in nature as well as real, right? The roots are real as well as repetitive, right? Real and repeated roots you will have, right? So the roots are placed at a distance of omega n from the real axis, like this. There are two roots at which place? Minus omega n, exactly, right? So see here, from here to here, what is the distance? It is omega n. From here to here, it is omega n, and from here to here also, it is omega n, which means all these roots are equally distant from the origin. We can say these roots can be connected by a semicircle like this. These roots can be connected by a circle whose radius is omega n, right? Whereas the roots which we have seen in the second case, they will also fall on this semicircle only. They will also be exactly on this semicircle only. You can consider them to be somewhere here, right? So see now, what are the real part as well as imaginary part of these particular roots? See here, the imaginary part of this root is omega d. It is j omega d, you can say, right? The real part of this root is minus zeta omega n. So if at all you are worried about its distance, whether it is its distance from origin is omega n or not, so let us look at that. Let us look at the distance. So let us draw a line from origin to this, right? So what is this distance? This distance is nothing but adjacent side squared. This is a right angle triangle, right? So within this right angle triangle, the right angle is here. So when zeta is exactly is equal to 1, the roots are real and equal, right? So these are the roots. So all the roots are going to be on the same semicircle. And let us not leave the other case also. Let us cover the other case also. So fourth case यहाँ पर देख लेते हैं. When zeta, that is case 4, when zeta is greater than 1. If at all zeta is greater than 1, then we are going to get s is equal to these two different roots only, right? S is equal to minus zeta omega n plus or minus omega n under root zeta square minus 1, right? These are the roots we are going to get, right? So in this case, see here, minus zeta omega n plus omega n under root zeta square minus 1 and minus zeta omega n minus omega n under root zeta square minus 1. So we are going to get two different roots, right? One root somewhere here and the other root somewhere here, because both the roots are real and unequal in this case, right? Roots are real and unequal in this case now. So it is just like the way you study different kind of roots for a quadratic equation for different values of d, where d is under root b square minus 4ac by under root b square minus 4ac, right? The same way, depending on zeta, you will get different values of different positions of these roots, right? So if zeta is greater than 1, these are the roots. So these are the root configuration, right? So when zeta is exactly is equal to 0, this is the case. I am going to represent each and every case here with this. When zeta is equal to 0, this is the scene, and when zeta is equal to 1 exactly, this is the scene, and when zeta is between 0 and 1, when zeta is 0 less than zeta less than 1, this is the case, and when zeta is greater than 1, this is the case. Zeta is greater than 1, right? So what if zeta is negative? There is one more case. What if zeta is less than 0, right? So the fifth case is when zeta is less than 0. So put some value of zeta which is less than 0. If zeta is less than 0, S will be what? This will be a positive number. Of course, if it is between 0 and 1, this will be a complex number, an imaginary number, right? So if at all zeta is less than 0, you will get roots in the right half of S-plane, right? Right half of S-plane means towards the right side of the j omega axis, right? In this case, you are getting all the roots towards the left side of the j omega axis, whereas if zeta is negative, you will get the roots to be in the right side of the j omega axis. So this is the case when zeta is less than 0. When zeta is less than 0, roots will be in the right half. So what happens if roots are in the right half? Do you have any idea if roots are in the right half, what happens? If roots are in the right half of S-plane, do you have any idea what happens? Yes, very good. If roots are in the right half of S-plane, the system will be unstable, and we are not interested in design of unstable systems. We are interested in analysis of stable systems, right? We are always interested in the analysis of stable systems. Of course, it is our point to see if a system is unstable, how to stabilize it, right? So we'll analyze that later. So we won't analyze for zeta less than 0. We will not analyze for zeta less than 0, right? So each and every case has a certain name. When zeta is exactly is equal to 0, this particular case, the response under this particular case will be called as undamped response. Undamped response. When zeta is between 0 and 1, this particular response is called as underdamped response. Underdamped response. When zeta is exactly is equal to 1, let me highlight this with some other color. When zeta is exactly is equal to 1, this response is called as critically damped response. Critically damped response, right? When zeta is greater than 1, this particular case will be called as overdamped response. Overdamped response. Is it clear, everyone? So let us look at what is this zeta, right? So what this zeta actually indicates. See here, in this case, let us say when zeta is between 0 and 1, so we have this particular right angle triangle like this, right? So we have this particular right angle triangle, and let us call this particular angle, this angle as theta, right? This angle is theta. Can you people tell me what is cos theta here? What is cos theta? In this right angle triangle, what is cos theta? So what is the vertical side? What is the length of the vertical side? Length of the vertical side is omega d. Omega d means, omega d is nothing but omega d is equal to omega n under root 1 minus zeta square. What is the length of this? Length of this is zeta omega n. And what should be the length of this? So in this right angle triangle, if you separate this particular right angle triangle here, right? So this length is zeta omega n. See, is it clearly visible? From here to here, it is this point is minus zeta omega n, this particular point, which means here to here the length is how much? Zeta omega n, right? From here to here, this vertical distance, how much is it? Omega d. This vertical distance is omega d. What about this? This is under root omega d squared plus zeta omega n whole squared, that is zeta squared omega n squared, right? So what is omega d? Omega d is omega n under root 1 minus zeta square. Therefore this is equal to under root omega n square multiplied by 1 minus zeta square plus zeta square omega n square. This will be is equal to what? This will be omega n. Right? That is nothing but omega n. See here, this omega n square minus zeta square omega n square. Both of them will get cancelled. And what is left? Under root omega n square. Under root omega n square means it is omega n, that's it. Right? So this is omega n. If this is omega n, what is the ratio? Cos theta. Cos theta, I am writing it here. Cos theta will be is equal to adjacent side divided by hypotenuse. What is adjacent side? Adjacent side is zeta omega n. And what about hypotenuse? Hypotenuse is omega n. Right? So cos theta is nothing but cos theta is equal to how much? Cos theta is equal to zeta. Cos theta is equal to what? Cos theta is equal to zeta. Right? So zeta is called as damping ratio. See here, it is a ratio of zeta omega n and omega n, right? So this is called as damping ratio. This is called as damping ratio. Zeta is called as damping ratio. So damping, what do you mean by damping? So whenever you study electrical measurements, what happens in that? See, when you study electrical measurements, you will use some eddy current damping, or else you will use some air friction damping, you will use some oil friction damping, right? Damping means it is a kind of braking, right? What is damping? Damping is a kind of braking, right? So braking means, so let us say what are the response of your system might be. Your system is tending to oscillate. Let us say your system is tending to oscillate, and you're applying some brakes on its oscillation. You're applying some brakes on its oscillation and you're bringing those oscillations to zero, right? So when the system is undamped, when zeta is equal to zero, right? When zeta is equal to zero, when your system is undamped, what happens is your system keeps on oscillating, right? You will apply some brakes, right? So when you increased zeta from 0 to some value greater than 0, what you're doing is you're applying some brakes. So in this case, what happens is your system oscillates a little and it finally settles down at a constant response, right? Whereas if you increase the intensity of brakes, what happens is your system's roots move this side, which means your system becomes critically damped. There is not even a single oscillation. There won't be any oscillations at all in your response, right? So if you apply the brakes very harder, right? If you increase the braking force, what happens to the response is the response itself will slow down, right? So we'll carefully see each and every case in these, right? So let us first observe the underdamped case, right? What we'll do is we'll first observe the underdamped case, that is when zeta is between 0 and 1, right? So after getting the underdamped response, from that we'll get each and every response very easily. Once we get the underdamped response, we'll get the remaining responses with ease. Is it clear? Is it clear till now?